Solve the polynomial inequality algebraically, and in this video we're going to demonstrate the boundary point method. The first thing that we need to do is to get 0 on one side of the inequality, which we already have. Then the other side of the inequality is going to be a polynomial. So what we need to do is to find the zeros of the polynomial that results on this side. Let's recall that the 0 of a polynomial is an x value that causes that polynomial to be equal to 0. And when we have a polynomial that is already in its factored form, as we do here, it's pretty easy to see who the zeros of this polynomial are. The zeros of the polynomial are going to be the x values that cause each of these factors to be 0. So the x value that causes this first factor to be 0 is going to be x is equal to -1. The x value that causes this second factor to be equal to 0 is x is equal to -3. And the x value that causes the third factor to be 0 is x is equal to 2. So we have found the zeros of the polynomial on this left-hand side. Now we're going to take these zeros and refer to them as boundary points. And we'll plot them on a number line so that we're separating the number line into separate intervals that we're going to be testing. So this doesn't have to be too precise with our number line. We're just basically using these zeros as what we're going to call boundary points that are splitting this number line up into 1, 2, 3, 4 different intervals. And now we're going to test these intervals to see which ones of them actually make true statements back in the initial inequality. So let's start by testing x is equal to -4 in this leftmost interval, which means that we're actually at step 4, that we're picking test values inside each interval to represent that region. So if x is equal to -4 works back in the original inequality, then the entire interval is also going to work. So here is the original inequality, and we're plugging -4 into all these x spots to see if this generates a true statement. -4 plus 1 is -3, -4 plus 3 is -1, -4 minus 2 is -6, and we want to see if that product is less than 0. -3 times -1 is +3, and then multiply that by -6 is -18. So since -18 is less than 0, this is a true statement, and therefore the interval containing our test value is part of the solution set. So now we're going to move into the next interval and pick some integer value if possible, and it is, we can pick x is equal to -2, which makes our calculation just a little bit easier. So we plug -2 in for all the x values. Again, -2 is being plugged into each of these x values back in the original inequality, and then evaluate to see if this is a true statement. So -2 plus 1 is -1, -2 plus 3 is +1, and -2 minus 2 is -4. And here -1 times 1 is -1, multiply that by -4 and we get +4, which is not less than 0. So this interval does not work. So now moving to the next interval, notice that 0 is in this interval, and that's always going to be my test value if the interval contains 0. So we're plugging 0 in for each of these x values, and here we go down here. 0 plus 1 is +1, 0 plus 3 is 3, and 0 minus 2 is -2. And this product is then going to give us -6, which is less than 0. So the interval that contains x is equal to 0 is going to be part of our solution set. So now our last test interval, let's grab the integer x is equal to 3. Again, we're looking for small integer values as our test point so that our calculations can be as simple as possible. And we're plugging 3 in for each of those x's and then determining whether or not this is a true statement. So 3 plus 1 is 4, 3 plus 3 is 6, 3 minus 2 is 1, and this is not going to be less than 0 because 4 times 6 is +24, which is not less than 0. So this is not true. This is a contradiction symbol here, and therefore this interval does not work. So now that we know which intervals work, it's time to also check the boundary points themselves. So let's begin with x is equal to -1. -1 when plugged in here is going to give us -1 plus 1, which is 0. And again, we plug -1 into all of them, so -1 plus 3 is 2, -1 minus 2 is -3. But since one of our factors is 0, this entire thing turns into a product that's equal to 0. and 0 is not less than 0. 0 is equal to 0, but not less than 0, so our boundary point of x is equal to -1 does not work. But actually, none of these boundary points are going to work, because when I plug -3 in, it's going to zero out this factor, causing the product to be equal to 0, which is not less than 0. So -3 is not going to work. And when we test x is equal to 2, plugging 2 in for all the x's, it causes this factor to be equal to 0, again giving us a product of 0, which is not less than 0, so this is not true, and 2 does not work either. So now it's time to state the solution interval, or the solution set. We saw that this interval here does work, and this interval actually begins way down at -infinity. So starting from -infinity and going all the way up to the boundary point, not the test point. So the boundary points are the values that divide up this number line. So we go all the way to the boundary point, but remember -3 didn't work, so -3 is not going to be part of the solution set. Then we skip over this interval because that one does not work. So this is our next working interval. Let's, in our interval notation, use the union symbol. Remember, -1 also didn't work, so it's not part of the solution set, but we do start with -1 because -1 is what begins this interval. Remember, we're not using the test points for this solution set, we're using the boundary point. So -1 did not work, and this interval starts at -1 and goes to +2, which also did not work. So it's not included in the solution set. And this interval out here did not work either. And this is all that's included in our solution set. Let's verify this answer by looking at the graph of the original polynomial. So this was the polynomial inequality that we started with. Let's consider y is equal to just the polynomial that's on the left-hand side of this inequality. So the output of this polynomial function is the same as the output of the left-hand side of this polynomial inequality. When graphing the polynomial function, we notice that it is a degree 3 polynomial with a leading coefficient that is positive, which means that the end behavior is going to be up in the first quadrant and down in the third quadrant. The x values that zero out these factors are the zeros of the polynomial, but they are also the x-intercepts on the graph. So -1 is an x-intercept, -3 is an x-intercept, and +2 is an x-intercept. Since all these factors have a multiplicity of +1, that means that our graph is going to cross the x-axis at each one of these x-intercepts. So let's begin down here in the third quadrant, come up to x is equal to -3, cross the x-axis there. We'll come up and turn around to approach the next x-intercept of -1, crossing the x-axis there. The y-intercept of this graph does turn out to be -6. If we plugged in 0 for all those x's, we get -6 as an output. So let's come on down and pass through that correct y-intercept. Turn around in a smooth and continuous way, and then cross through the x-axis again here at x is equal to 2. Now this is a very rough graph, but it is enough for us to see where the function is positive and where it's negative. We want the output of this polynomial to be negative, which means that we're looking for the y values that are negative. And the y values of this polynomial function are negative in this region and then also in this region. So the solution to this polynomial inequality is going to be all the x values starting way out here at -infinity. All these x values generate negative y values, and going all the way up to -3. But we're not going to include the -3 because at -3 we have a y value of 0, and we want our y value to be strictly less than 0. So then we skip over this region because these have positive y values. And this interval is the next interval over which the y values are negative. So we use the union symbol. Our interval starts at -1 and ends at +2. So from -1 to 2, remember we're not including either one of those because at -1 the y value is equal to 0 and at 2 the y value is equal to 0. So this graph confirms that we do have the correct solution set.